Hello, everyone. Welcome to this room here. It's great to see all of you here. It is my great pleasure to talk to you about Project Hydrogen, which is really now a big community effort to unify all the efforts made by the big data community along with the AI community. So I see a number of people still coming in. There's plenty of room over there if you want to move further over there. So. I've been working with Spark for quite a while. Mostly, I've been using deep learning and machine learning with Spark for a couple of years now, and I am one of the co-authors for deep learning pipeline and for TensorFrame. So a number of frameworks that already try to combine deep learning and Spark. I also want to mention that this talk is co-authored with Shangri Meng, who could not come here today. And he has heavily contributed to all the technical effort to build Project Hydrogen, along with Reynolds Sid and a number of the other members of the community. So really, this is London. I don't want to talk to you like Dickens about the tale of two cities, but I want to tell you about the tale of two communities here. One for the big data community, which has been building large solutions for handling large amount of data, and then has been starting to focus more with how to apply AI and machine learning and deep learning to build applications. And the other one, which is the deep learning community, which started by trying to solve extremely challenging problems using machine learning, and then realized that they needed more and more data to solve that. And if you look at the history of the two projects, you can see really how they're converging together. From a perspective of Spark, Spark started really first as I would say, well, at least when I used it, started as a proof of concept to show that you could distribute computations in an efficient and interactive manner. And from that, each of these communities at about the same time started to work on simplifying and also on scaling out and improving the performance of their frameworks. So from a perspective of Spark, this looked like first from the RDD-based API in Scala, which then moved to the more general data frame-based API. And then, once it had this very generic, simple API for the users, it could then go down inside the technology and simplify a lot of the internals to make them more efficient and faster. So this is where this led to the genesis of Project Tenston, which still continues to these days, to improve the performance of Spark without having the user to change its APIs. And then, of course, this moved further and further into continuous processing to handle streaming. So from the perspective of the AI and the deep learning and machine learning communities, you can see also a similar pattern, where it started by establishing foundational libraries, such as NumPy, SciPy, and then building blocks, specific machine learning blocks on top of that, such as XGBoost or GLMNet, specialized libraries to work with to work in the machine learning space. And after that, you saw an effort to build around some toolboxes, some more generic toolboxes around that, such as scikit-learn, which is a project from INRIA and Google. And then as it moved into larger and more complex problems, and as it moved into trying to solve problems with deep learning, we saw again the same patterns, where TensorFlow and Torch and the other libraries were foundational libraries, which were fairly hard to use, but were extremely performant for the hardware they were targeting. And on top of that, you start to see some other abstraction like Keras, which simplified a lot the usage of these deep learning libraries. And finally, now we are arriving at a point where these libraries try to be also not only simpler, but also faster for the hardware they have, such as the XLA effort from TensorFlow, and also try to leverage more hardware and more data. And really, if you look at these two communities, you start to see how they combine actually, how they start to converge toward the same goals. So when you look from the perspective of AI, you can clearly see now that AI needs a lot of data to be efficient. And this is rendered by this popular curve here, where somehow to simplify and I hope that all the machine learning experts here in the room will forgive me by saying that at some point, if you lose classical machine learning, it tends to plateau as you give more data. But somehow it reaches some infinity and beyond if, in performance if you're using deep learning. This is a bit of the popular opinion, but it is seen as actually, the deep learning is really seen as an effective technique as long as you can provide a lot of data to it. So this is why you see now more efforts in the deep learning community to represent and manipulate large data sets. And for example, now TensorFlow has its own API to represent data sets, the tf.data and package, and then the tf transform also module for representing the transforms on this data set. And also a number of connectors to build and integrate with other big data systems. And from the perspective of big data, we also need AI now to tackle more and more complex problems. And nowadays, you saw you heard this morning from the CDO of Ordnance Survey, where she was trying to use all the data that she was using from geospatial analysis, for example, and this require using deep learning to get state-of-the-art results. So this is why you have a lot of frameworks that have been developed from the perspective of the big data community. And so far, I think some of the prominent ones, I would say, are probably the effort from Yahoo with Caffe on Spark and TensorFlow on Spark. And Intel also has shown how you can use their CPUs efficiently for doing deep learning with big DL. And there are also a number of efforts, such as Spark NLP. Databricks has contributed a number of packages with TensorFrame, Spark Deep Learning. And also, if you count all the other packages, there is also a lot of other packages around that. So what I would like to tell you now about is, I would say, some of the most common stories that we see when these two worlds come together from the perspective of the users of Spark, whom we hear about, whom we hear from, and also from the customers of Databricks who present to us the problems they have when they try to combine these two together. So typically, when we see data scientists trying to build deep learning pipelines, where they start from a store containing some data. Usually, it's a massive store, and it can be on S3, it can be on Blob Store, it can be on their own databases, and they try to build deep learning models from that. And because they have so much data, they want to be able to leverage multiple machines for doing that. And once they have trained a model, it is typical to try to use it in a production setting on streams of data to have really good latency when you have new data coming in. And so once they have trained a deep learning model, they want to be able to pass it to a streaming system. And this is really hard to do these days. Why is that so? So if you look at how you can communicate data from a data warehouse to a system that can train a deep learning models, typically, you'll have to load this data, and this data is usually not represented in a form that is directly usable by a deep learning framework. Typically, it is stored in some proprietary format, or it is stored in Parquet, or it is stored in different, or in some other formats. And you want to be able to represent it in a certain way to use it. And the glue that people tend to use for that is Spark, because Spark can read from more than 50 different sources and write to more than a dozen. But also, you need to be able to use a GPU cluster. And for that, you have some frameworks that have been developed, such as Harvard, distributed TensorFlow, and so on. But in order to communicate data to this dedicated cluster, you need to write a lot of glue code. And as a data scientist, you don't want to spend your time writing all the glue code that is necessary to move data from data warehouse to a GPU cluster. And you have the same problem when you want to do, for example, inference in a streaming fashion. Because if you look at TensorFlow, well, you don't have an interface inside TensorFlow to say read from a Cascade tree. And typically for that, people use something like Spark to be able to load data from their stream and then pass it to the prediction part in order to run the computations, to run the prediction. And for doing that efficiently, it is common to do that on the GPU cluster. And combining all of these pieces together here, this takes a lot of effort, and this takes a lot of code complexity to be able to move that. So Project Hydrogen came here to be able to simplify all the components inside Spark that were required to make this communication as efficient as possible, and also to simplify the interface from the perspective of the data scientist and from the perspective of the end user. So why is it so complex to do that? So if you look at Spark, Spark is, and as Renal was presenting this morning, Spark is meant to run tasks in parallel. And while if you look at this distributed training system, they are meant to communicate and share states between each of the machines. They require coordinations. So if one machine crashes in the case of Spark, it's easy. You just restart, you rerun it, and you know that you will complete it. In the case of distributed training, you need to do you need to do something different. You need to restart from a checkpoint, and you cannot simply respawn a machine. You need to restart from a checkpoint and then rerun the computations from this point on. So Spark Hydrogen came really when we look at these two paradigms, and Spark Hydrogen came into being when we realized we needed to bridge these two paradigms together in a way that was effective in terms of performance and also simple from the perspective of the user. So I would say there are three parts that I want to talk to you about for this umbrella project. One of them is the barrier execution mode, which we talked about this morning already at the keynote. The other one is optimized data exchange. Explain to you what needs to happen inside Spark to make this data transfer as fast as possible. And finally, what the new efforts that we're developing and we're doing with other communities to make sure that Spark is aware of the hardware under the hood and can efficiently schedule tasks to use optimally this hardware. So let's talk first about the barrier execution mode. So this is what is called gang scheduling in the numerical computing community, where essentially just like a gang, either you have the whole gang or you have nobody. You don't have one or two turncoats. So this is how you want to run a distributed training job. So this is mostly implemented in Spark 2.4, but we'll see more of this work and in a more efficient manner for Spark 3.0. And there are actually a couple of developers in the room whom you can talk to after that. So what does it look like in practice? What does it mean? So we added to the Spark API, to the RDD API, both in Scala and in Python, a couple of new concepts. One of them is the barrier mode, to say that all the tasks that are going to be executed on this RDD has to be scheduled all together, and then they need to be finished all together. So Spark will just wait for all the allocated slots before it can start to execute all the tasks together. And also inside this task, they will have access to more information about how the other tasks are being set up and distributed on the other machines. So the barrier task context will provide the information required, such as the IP addresses, how to communicate with the other machines, and also the technical capabilities of the other machines. The other piece which is critical in that space is the concept of barrier. So this is not new. This is already primitive in MPI, for example. And this primitive allows the users to block and synchronize for all the tasks to complete one step before it can move on. And I will show you in practice what it looks like when you want to put it in action. So here is a typical way of how to use it. I'll show you in the code what it looks like. But so for example, in the case of MPI, if you want to run a Harvard job using MPI, you would have a master, which is not the Spark driver. It can be another machine. It is spawned by another task. And this master will retrieve all the information about the other workers that are around it, schedule some work on this machine, and in the meantime, all the other machine will wait for the barrier to be reached, so for all the work to be completed. And once this barrier is reached by all the machines, they will be allowed to proceed and continue to work afterwards. So of course, we found out that you can implement that pretty easily in Spark already. There are a couple of things that actually turn out not to be easy, and one of them is setting up the communication channels. For example, if you want to use MPI, the standard way of communicating with the other machines is to use SSH. And creating some new keys on the fly and communicating the exchange, especially without being able to use the primitive of Spark for doing that, turned out to be a challenge. So this is why we are working with the different cluster manager communities to make sure they can expose enough information inside Spark to be able to deal with setting up the authentication and the communication channels with the other machines. So let's talk a bit about data exchange, and then I'll show you what it looks like in practice inside the demo. So you need to have data exchange because otherwise you have data coming from Spark, and then you are stuck. Then you have to write it somewhere, and then you hope that it's going to be read by some of the other machines. But it prevents users from directly communicating efficiently their data that they have already processed through ETL to these deep learning frameworks. So typically, people use a user-defined function for doing that. And as Reynald mentioned this morning, the performance, if you want to do that with a user-defined function, is really bad. Because if you work on a row-by-row level, the most of the time will be spent on the overhead for dealing with that. So how much overhead are we talking about? We talk about something like 90% to 99% of the time spent simply on the data exchange. So even if Python is slow, sending data to Python is even slower than that. And this is where you would, so most of the time would be simply spent communicating with Python here. So this is where the vectorized data exchange, also commonly called the Pandas UDF, comes into play. So in that case, we simply send directly all of a row of data onto Python, and then we retrieve, and then Python retrieves it, processes it, and then moves it back on the other side. So of course, when we talk about sending something back and forth between different stacks, that means establishing a protocol. And it turns out that the Arrow community that was solving the same problem around Pandas was very proactive into establishing a standard that we could use for communicating this data set in an efficient columnar fashion between Spark and between Pandas, for example. So what does it look like in practice if you want to use it inside your code? So you don't need to do much. Instead of working on a row-by-row level, what you would do is declare that this data frame has to be used as a Pandas data frame, or as an Arrow, as a Pandas RDD or as an Arrow RDD. And from that, you can get access directly to batches of data. Behind the scenes, Spark will take care of taking data from its own internal format, which can be either row-based or columnar-based, and convert it to column vectors and send it to your computations. And this works both for Python and Scala. So we showed some results. But essentially, if you do that, you can get sometimes speedups by 200 or 300 times compared to just working on the row-by-row level. So this is really significant. And also, from a user perspective, it is usually not much of a change, because it is typical to start by prototyping with Pandas. And here, that means you can reuse all this Pandas code directly inside Spark without having to rewrite it in a way that would be using the row-based API for Spark. So let me show you what it looks like if you want to use it in practice. This is using an unreleased version of Spark, but that is going to be representative of what you see inside Spark 2.4. So I have here a cluster running Hydrogen, and I have 4 workers. So this is a GPU cluster, P2X large machines running 4 workers. And what I'm going to do, what I would like to do here, is that I would like to run on this cluster. I like to run. Let me start the computations. So I like to run the computations on 2 machines to be able to train a model. And here I'm going to use a distributed framework, Horvath, to use these machines. And in the meantime, I would like to be able to use the models I'm creating to build a model inference, to use this model, and then plug this model inside a stream and run this stream for computing some result here, some digits, and also using these GPU machines. So this is what it would look like if you're not using Hydrogen. So I have a table here that loaded the data. And since I want to use 2 machines, I am repartitioning it. And I'm writing the results onto a distributed file system. And I'm running Horvath here. OK, so it is running. And here I'm using Spark to distribute the calculations onto 2 machines. So I got access to 2 machines, and now it's running. OK, so now if I want to do model inference, so this is always the beauty of running live demos. You never know really if it is going to work as expected. But OK, this looks like it's working. So here I'm using my stream of digits. And I'm calling here and I'm building this data frame where I'm calling on these features. I'm calling a GPU. I'm using a GPU to use an existing model, compute some predictions, and then build a new stream out of that. So what I get here is some label, which corresponds to what I had, and then the prediction I'm making. So I'm trying to run it. And actually, what happened here is that it didn't work. So the reason why it didn't work is because Spark was not aware of which machines, which GPUs we're using. Spark was not able to gather just from the information it was given that some of the machines' GPUs were already being used by the training system. So it tried to schedule everything onto the 4 workers, and then it failed on 2 of the workers. OK, so if you want to solve that, eventually, without Spark 2.4, without Spark Hydrogen, you would need to either have dedicated clusters with all the overhead that it comes with it, or you would need to build some complex logic under the hood to be able to separate which machines are running with which machines' GPUs are being used and which one are not being used. OK, so here I'm going to clean my cluster, and I'm going to show you what it looks like with the Project Hydrogen. So again, I'm going to run here my code. And this time I'm using the new APIs. So again, I'm making 2 partitions to be able to use 2 machines only. I'm converting all these partitions into Pandas representation inside the RDDs. And then I'm calling the barrier mode here to say that all the computation that's going to happen will happen here inside will be run inside Horvath in a distributed fashion using these 2 machines. OK, so it looks like it is starting. And now it is running as a Spark job. And Spark sees here that it has 2 machines, two tasks being launched to run that. OK, and now let's use the model that we are training in our stream to see what we can infer. So this is the same code here. I'm not changing anything. And this time let's see if the stream works. So one thing to notice here is that Spark here is aware that it can only use 2 machines. Running only 2 machines, it's only launching 2 tasks at a time, and then it will wait to get access to the machine when they're cleared. OK, so we should start to get some results soon. OK, and OK, so it should come anytime now. But OK, here we go. So now we start to see our predictions coming from our deep learning models, and this is in the meantime we still have our inference jobs running here. So using Project Hydrogen, I was able to partition my cluster of GPUs into a number of machines using the GPUs for running distributed deep learning for training, and the other ones were used for my regular task, but still using GPUs for running for running calculations on these. OK, so of course to make it work, we need also to think about clusters that are not only having GPUs but also other hardware capabilities, and also that are more heterogeneous when they want to do that. So this is the goal of this SPIP here, Spark 24615, which is a prototype, which for now is a suggestion on how Spark could, and how Spark users could express their requirements for saying, they want to have GPUs, or they want to have FPGAs, or other special capabilities, and to instruct Spark to just run tasks on these machines. So far, the API would look like this. This is still tentative. And it would mention here, for example, if I want to have 2 tasks running on each of the GPU machines, it would instruct Spark to be able to, this is how you would express this dependency here and these requirements. And also, since a number of frameworks have the ability to fall back, of course at the cost of performance, but since a number of frameworks can fall back onto regular hardware like CPU, you can also specify whether you can, whether you should absolutely use GPUs, for example here, or if you can still use regular CPUs and then simply not have an accelerated calculation. And of course, this machine, that once you reach inside the task, typically you have several tasks scheduled on the same node, especially if you start to have multi-GPU machines. So you'll have access to all the information about which task has been scheduled on which GPU inside another context that you can retrieve inside the task. So the API is still pending discussion, and actually, I would love to have some discussion with people who are interested or who would like to use this API to see what would be the best requirements for that. And again, here, this will require cluster manager support. So this is already implemented in Spark standalone, and we're looking with the different communities with Mesos and Yarn to see how they can export this information to Spark. So this barrier mode, a first preliminary example is coming here for Spark 2.4. I just showed here Harvard integration with Spark 2.4, but we are looking at how we can rationalize and simplify the API even more, so that we can offer this support in a stable manner inside the Spark 3. Okay, so this would not have happened without a lot of other projects in the community, and here we are really gathering a lot of effort that already happened. So this is really here, I really want to emphasize the fact that this is a community-led effort. And a lot of committers and contributors whom I've seen around the room already have been helping in this fashion. So thanks a lot. I think we have time for a few questions. Okay, any questions?
Thank you, Tim.
You have this concept for the vectorized data frame or something, and you only mentioned that, I mean, at least in the slide I saw, you mentioned about UDFs, let's say. But does it also work for UADF, like user-defined aggregated function, or is it like the different thing altogether?
Yeah, that's a great question. So as part of Spark 2.4, there is going to be some effort to simplify the Pandas, so the vectorized UDF and UDF implementation. Actually, if you look at the ticket, which is linked here, I think. There is actually, you can see some of the work, some of the proposals that are being made to simplify the work around using UDF for that. And I think we're going to see actually more and more work done on vectorizing different pieces of the engine and exposing that information, simply because it brings so much performance benefit after that. So the UDF was the first target, because this is critical for doing any deep learning application, but UDF is definitely the next one for doing that.
Do you also have this function also in 2.2, or is it just available from 2.4, the vectorized concept?
So you can already use, if I remember correctly, you can already use Pandas UDFs in Spark 2.2, if I'm not mistaken. But starting from Spark 2.4 and forward, this is going to be where the API is going to be deemed stable enough for general use. Okay.
We have time for
Question?
one more question.
Hi. So does all this announcement mean that you are more and more promoting the PySpark API in comparison to the Scala API? Because I understand that all this won't be able on Scala, but only on Python.
So this is the Scala syntax here, and
Sorry,
that's made on purpose. But yes,
the pandas and all this are.
Yeah, so this is going to happen both in Scala and Python. And actually, the implementation behind the scene is, of course, in Scala and Java. The reason why the example was in Python is because the deep learning community has settled, for better or for worse, on Python as being the language, the de facto standard for expressing the deep learning, for expressing deep learning pipelines. And this is why, if you want to be able to integrate with this, with all the efforts from the AI community in general, the Python interface needs to be as good a citizen as the Scala API. And this is why also we are targeting as first application some Python-based API. But that being said, all this interface here is going also to be available in Scala and Java. And also this is how we plan to eventually see how we can also integrate it with the other language supported by Spark, which is R.
All right, thanks again, Tim.